Something is synchronizing, and nobody wants to say it out loud. Taiwan just recorded a magnitude 6.6 earthquake, 150 kilometers deep, in rock that shouldn't be breaking. The sun is throwing X-class flares at Earth like it's trying to get our attention. And in less than 2 weeks, 7 planets will compress into a geometric configuration we haven't seen since 1936. Coincidence? Maybe. But then there's the Visitor, an interstellar object called 3I Atlas that survived temperatures that should have vaporized it, now sporting a coma larger than Jupiter and barreling toward the exact center of this alignment. The patterns are clustering, the cycles are converging, and if you think this is just fear-mongering, stay until the end, because what's happening in the solar system right now might rewrite everything we thought we understood about cosmic timing. Subscribe now and follow along, because you'll want to be here when the planetary alignment peaks in January, when the solar maximum intensifies, when the tectonic stress windows open, and what we're actually witnessing, this synchronization of cycles, becomes impossible to dismiss as mere coincidence. The ground beneath Taiwan moved on a Tuesday morning, and nobody expected it. A magnitude 6.6 earthquake struck deep, roughly 150 kilometers below the surface, far enough down that most people would never think twice about it. Most earthquakes we hear about happen in the first 30 kilometers of crust, where the plates grind and snap like frozen branches. Those are the ones that topple buildings and crack highways. But deep earthquakes are different. They happen where the rock is so hot and compressed that it shouldn't be brittle at all. The fact that it breaks anyway tells you something is profoundly wrong with the stress distribution in that part of the planet. Taiwan sits on one of the most geologically volatile stretches of real estate on Earth. The Philippine Sea Plate is shoving itself beneath the Eurasian Plate at about 8 centimeters per year, which sounds slow until you realize that's the width of your hand every decade, and it's been happening for millions of years. The island is essentially a crumple zone, a place where the planet's skin folds and fractures under relentless pressure. When a deep earthquake hits there, it's not just a local event. It's a pressure gauge going off. It's the Earth telling you that stress is building in places you can't see, in the mantle itself, where the real action happens. Think of the crust as a thin shell floating on a semi-molten interior. When stress accumulates at depth, it means the forces driving plate tectonics are intensifying, that the engine beneath our feet is running hotter, or faster, or both. Deep focus earthquakes are relatively rare compared to their shallow cousins, which makes them statistically significant when they occur. They're often precursors, warnings that the system is approaching a threshold. And here's the thing, this didn't happen in isolation. While Taiwan was shaking, the sun was throwing tantrums. Multiple M-class solar flares erupted in late 2025, followed by several X-class flares, the kind that makes satellite operators nervous and astronauts take cover. These flares send waves of charged particles screaming toward Earth at millions of kilometers per hour. When they hit our magnetosphere, they compress it, squeezing the protective bubble that shields us from cosmic radiation. Airlines reroute polar flights, GPS systems drift, power grids in northern latitudes brace for induced currents that can fry transformers. The sun operates on cycles, roughly 11 years from one peak of activity to the next. We're currently in solar cycle 25, and we're approaching the solar maximum, the period when the sun's magnetic field is most chaotic. Sunspots proliferate, magnetic field lines tangle and snap, and the result is an uptick in flares and coronal mass ejections. This is normal, predictable even, but the intensity of late 2025 has been noteworthy. Several of the X-class flares ranked among the most powerful of the current cycle. So, we have tectonic stress and solar fury happening almost simultaneously. Coincidence? Maybe. But then you look at the calendar. January 2026 is less than 2 weeks away, and in that month, something unusual happens. The Sun, Mercury, Venus, Earth, Mars, Jupiter, and Saturn will arrange themselves in a near-linear configuration, compressed within a narrow band of heliocentric longitude. It's not a perfect straight line. Nothing in space ever is, but it's close enough that astronomers have been quietly noting it for months. The last time we saw a planetary alignment this tight was 1936, nearly 90 years ago. Now, before you roll your eyes and think this is astrology dressed up in a lab coat, let me be clear. This is not about cosmic destiny or zodiac prophecies. This is about gravitational stress, electromagnetic coupling, and resonance effects that mainstream science is only beginning to take seriously. The moon and the sun dominate Earth's tides. That's Astronomy 101. But when multiple planetary bodies align, even their relatively weak gravitational fields can create cumulative effects, especially if Earth is already under tectonic load. Think of it like this. If you're holding a heavy weight and someone taps your shoulder, that tap doesn't make you drop the weight. But if you're already trembling, already at your limit, that tap might be enough. And if you think a deep earthquake and some solar flares are just background noise, just the planet doing what it always does. Consider this. Scientists have a term for when events cluster together more tightly than random chance would predict. They call it temporal clustering. It's the universe's way of saying, pay attention. Statistical analysis of seismic activity has shown that earthquakes don't always follow a purely random distribution. Sometimes they bunch up. Sometimes a major quake is followed by aftershocks that continue for weeks or months. Sometimes different fault systems seem to trigger each other across thousands of kilometers. The mechanisms aren't fully understood, but the patterns are undeniable. When you add solar activity into the mix, when you factor in magnetic field variations and ionospheric disturbances, the picture becomes even more complex. But here's where it gets truly strange. While Earth is rumbling and the sun is raging and the planets are lining up, something else is out there. Something that came from outside our solar system. Something that survived a close encounter with the sun when it absolutely should not have. Something that is now sporting a coma larger than Jupiter and a tail that stretches farther than the distance between the Earth and the Moon. Its name is 3I Atlas, and it's heading straight toward the gravitational center of this cosmic convergence. Discovered by the Atlas Survey System in 2025, this object has defied expectations at every turn. It's not behaving like a typical comet. It's not following the script we've written for icy visitors from the outer solar system. And it's certainly not acting like something that's been frozen in interstellar space for millions of years. And while Earth and the Sun are already reacting, this interstellar intruder just survived the Sun. And it shouldn't have. Let's talk about what happens when planets line up, and why this isn't the fantasy you might think it is. On January 2026, 7 major bodies in our solar system will occupy a remarkably narrow slice of space when viewed from the Sun's perspective. Mercury, Venus, Earth, Mars, Jupiter, Saturn, and the Sun itself will be compressed within roughly 40 degrees of heliocentric longitude. To be clear, they won't form a literal, straight line. Space doesn't work like that. Planets orbit at different inclinations, at different distances, and at different speeds. But they'll be closer to linear geometry than they've been in nearly 9 decades. Imagine looking down at the solar system from above the Sun's North Pole. Most of the time, the planets are scattered around the Sun, like numbers on a clock face. But in January 2026, they'll bunch up, occupying roughly the space between 10 o'clock and 2 o'clock. That's compressed. That's unusual. Now, classical physics will tell you this doesn't matter. The Moon and the Sun create tides that dwarf anything the planets could produce. Jupiter, despite being the most massive planet, is so far away that its gravitational pull on Earth is negligible, about 1,000th the strength of the Moon's. If you calculate the raw Newtonian force, planetary alignments look like cosmic non-events. The numbers don't lie. The gravitational influence of Mars on Earth is weaker than the influence of the truck driving past your house. But force is not the same as stress, and this is where the controversy begins. Imagine you're holding a rope stretched taut between 2 points. If someone pulls it from the side, even gently, the entire rope responds. It doesn't take much force to change the distribution of tension. Earth's crust is not a solid shell. It's a fractured, dynamic system already under constant stress from plate tectonics, mantle convection, and thermal expansion. When you add even a small additional gravitational vector, especially during a period when stress is already elevated, you might shift the timing of events that were going to happen anyway. This is not about planets pulling buildings off their foundations. This is about resonance, about small periodic forces aligning in ways that amplify existing instabilities. Think of pushing someone on a swing. You don't need to push hard. You just need to push at the right moment, in rhythm with the swing's natural frequency. A small force applied at the right time can produce a large effect. And then there's the electromagnetic angle, which is even more speculative but increasingly harder to dismiss. Planets generate magnetic fields. These fields interact with the solar wind, creating bow shocks and magnetospheric disturbances. When multiple planets align, their collective influence on the sun's heliosphere, the bubble of solar wind that surrounds the entire solar system, could theoretically create compression waves, density fluctuations, and electromagnetic pulses that propagate back toward the inner planets. Earth's magnetosphere would respond to these shifts, and since the magnetosphere couples to the ionosphere, and the ionosphere couples to atmospheric and oceanic currents, you have a potential cascade of interactions. Is this proven? No. Is it ridiculous? Also no. The problem is that we don't have enough data. Planetary alignments of this magnitude are rare. The last comparable one happened in 1936, before we had satellites, before we had magnetometers in space, before we had the computational tools to model complex multi-body gravitational and electromagnetic interactions. We're essentially flying blind, trying to understand a phenomenon that occurs once every few generations. In 1936, the last time we had an alignment, this pronounced, Earth experienced heightened seismic activity in certain regions. The data is patchy, record-keeping was inconsistent, but there are reports of increased earthquake frequency in the months surrounding the alignment. Correlation is not causation, and scientists are right to be skeptical, but humans didn't evolve to ignore patterns. We notice synchronization because sometimes synchronization matters. The reason mainstream science avoids planetary alignment claims is simple. The field is littered with pseudoscientific garbage. Every few years, someone predicts an earthquake or a pole shift based on astrology, and when nothing happens, it discredits legitimate questions. But behind closed doors, some physicists are quietly running simulations, studying resonance effects, exploring whether gravitational and electromagnetic interactions might create windows of elevated probability. They're not saying the planets will cause disasters. They're asking whether the planets might modulate the timing of disasters that are already building. It's a subtle distinction, but it's crucial. The energy for an earthquake comes from tectonic stress accumulated over decades or centuries. The alignment doesn't create that energy, but it might influence when and where that energy gets released. There's also the question of tidal forces on the Earth's interior. We usually think of tides as oceanic phenomena, but the solid Earth experiences tides too. The crust rises and falls by as much as 30 centimeters in response to the moon's gravity. These Earth tides create stress variations in the crust that, in theory, could influence the timing of earthquakes on faults that are already close to failure. If planetary alignments enhance these tidal stresses, even slightly, they could shift the probability distribution. And while we're asking uncomfortable questions about celestial mechanics, let's add one more variable to the equation. What happens when you throw an interstellar object into this mix? An object that defies expectations, that behaves in ways we don't fully understand, that is barreling through the exact region of space where this alignment is taking shape. Now add something that doesn't belong here at all. Interstellar objects are rare, and the fact that we've detected 3 of them in the last 8 years should tell you how far our observational technology has advanced. 3I Atlas is the 3rd confirmed visitor from beyond our solar system, and it's nothing like the first 2. Oumuamua was a cosmic mystery wrapped in silence, a dark, elongated object that tumbled through the inner solar system without a tail, without outgassing, without any of the theatrics we expect from comets. Its elongated shape and slight acceleration as it left the solar system sparked intense debate. Some argued it was a hydrogen iceberg, others suggested nitrogen ice, and a few, most notably Avi Loeb, proposed it might be artificial, a light sail from another civilization. Borisov was more conventional, a comet-like object that behaved exactly as you'd expect, glowing and shedding material as it warmed near the sun. It looked like comets from our own solar system, just visiting from elsewhere. 3I Atlas is something else entirely. Its orbit is hyperbolic, meaning it's not gravitationally bound to the sun. It came from interstellar space, it's visiting, and it's leaving. It reached perihelion, its closest approach to the sun, on October 29th through 30th, 2025. At that point, it was roughly 112 million kilometers from the sun, well inside Earth's orbit. For an object that spent millions, possibly billions of years drifting through the freezing void between stars, this was a baptism by fire. Most astronomers expected it to disintegrate. Comets are fragile. They're not solid rocks, but loose aggregates of ice, dust, and organic material held together by gravity that's barely stronger than static cling. When they get close to the sun, the ice sublimates, turning directly from solid to gas, and the whole structure can fall apart. The pressure from outgassing can create cracks. Thermal stress can shatter the nucleus, and the whole thing can crumble like a sandcastle hit by a wave. Comet Shoemaker-Levy 9 broke into more than 20 fragments before it even reached Jupiter. Comet Ison disintegrated as it grazed the sun in 2013, streaming away as a cloud of debris rather than a coherent object. Long-period comets, the ones that visit from the Oort cloud on their first approach to the sun, are especially vulnerable because their ice hasn't been heat cycled before. 3I Atlas was supposed to follow the same script. It didn't. Instead, it survived, and then it intensified. By mid-December 2025, as it made its closest approach to Earth at roughly 1.8 astronomical units, about 170 million kilometers away, astronomers observed something extraordinary. The object had developed a coma, a cloud of gas and dust surrounding the nucleus that measured approximately 185,000 kilometers in diameter. To put that in perspective, Jupiter is about 143,000 kilometers wide. This interstellar visitor was now wearing a cloud larger than the biggest planet in our solar system. And it didn't stop there. The tail, the stream of material being blown away by solar wind and radiation pressure, stretched to roughly 400,000 kilometers. That's longer than the average distance between the Earth and the Moon. If you could see it with the naked eye, it would dominate the night sky, a spectral banner stretching across a significant fraction of the celestial sphere. But here's where it gets weird. Observers also detected an anti-tail, a spike of material that appears to point toward the sun instead of away from it. Anti-tails are optical illusions caused by the geometry of the dust trail and our viewing angle, but they indicate that the object is shedding material in complex, non-uniform ways. The dust particles released by a comet don't just blow straight back. They spread out along the comet's orbit, creating a curved sheet of debris. When Earth passes through the plane of this debris sheet, we see it edge on, and it can appear to point in strange directions. Add to that the fact that spectroscopic analysis revealed wobbling jets, streams of gas erupting from different parts of the nucleus at different times, suggesting rotation and internal asymmetry. Comets don't outgas uniformly. They have active regions, patches where ice is exposed to sunlight and sublimates rapidly, creating jets that can actually change the comet's rotation or even alter its trajectory slightly through rocket-like thrust. This is not a simple iceberg melting in sunlight. This is a dynamic, active, structurally complex object undergoing processes we don't fully understand. The size of the coma suggests enormous amounts of material are being released. The persistence of the activity this far from the sun suggests either unusual composition or a large reservoir of volatiles. And it's not done yet. On March 16, 2026, 3I Atlas will cross Jupiter's orbital distance at roughly 0.357 astronomical units from the giant planet. It won't collide, but it will pass close enough that Jupiter's immense gravity could perturb its trajectory, potentially revealing more about its mass and composition. If the object's path bends more, or less than expected, that tells us something about how much mass it contains, which in turn tells us about its density and internal structure. But here's the question nobody wants to ask out loud. Why is it behaving this way? Why is an object that should have been destroyed, or at least severely degraded, still putting on a show that rivals anything we've seen from solar system comets? The answer is, we don't know. And it's moving toward the gravitational center of the solar system, right as everything else lines up. Science is built on anomalies, on observations that don't fit the model, and 3I Atlas is serving up anomalies like a buffet. Let's start with the composition. Spectroscopic analysis of the coma shows it's rich in carbon dioxide. Carbon dioxide outgassing is not unusual for comets, but the timing is. 3I Atlas is now far enough from the sun that water ice sublimation should dominate any activity. Water ice sublimates at temperatures above about 190 Kelvin, while carbon dioxide sublimates at much lower temperatures, around 150 Kelvin. This means carbon dioxide should be stripped away first, closer to the sun, while water ice continues to outgas as the comet recedes. The fact that we're still seeing significant carbon dioxide emission suggests either an unusually high concentration or a subsurface reservoir that's only now being exposed. Maybe the initial heating near perihelion created cracks in the nucleus, exposing deeper layers of ice that are now sublimating as the object cools. Or maybe the carbon dioxide to water ratio is fundamentally different from what we see in solar system comets, a compositional signature of its interstellar origin. Then there's the polarimetry data, which sounds technical, but is actually quite simple. When light scatters off particles, it becomes polarized, meaning the light waves oscillate in specific directions. By measuring this polarization, astronomers can infer the size, shape, and composition of the particles in the coma. Most comets show positive polarization values, meaning the scattered light is polarized in predictable ways based on standard dust models. 3I Atlas shows unprecedented negative polarization in certain wavelengths. This is rare. It suggests the dust particles have unusual optical properties, possibly because they've been heavily processed by cosmic rays during their long journey through interstellar space. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that bombard objects traveling between the stars. Over millions of years, this radiation can alter the molecular structure of surface materials, creating exotic chemistry that we rarely see in solar system objects. It can break chemical bonds, create new compounds, and change the way materials interact with light. Think of it like wood that's been weathered for centuries versus freshly cut timber. The surface chemistry is different, the texture is different. The way it reflects and absorbs light is different. 3I Atlas has been weathered by the harshest environment imaginable, the interstellar medium, where temperatures hover just a few degrees above absolute zero, and radiation bombardment is constant. This brings us to the uncomfortable part. Avi Loeb, the Harvard astrophysicist who has never met a controversial idea he didn't want to interrogate, has pointed out that the anomaly density surrounding 3I Atlas is higher than we'd expect from a purely natural object. He's not claiming it's artificial. He's not saying it's a probe or a derelict spacecraft. He's saying that the combination of survival, size, activity, composition, and polarimetry results is statistically unusual, and that we should be studying it far more aggressively than we are. Loeb has been making similar arguments about Oumuamua for years, pointing to its acceleration, its shape, its lack of observable outgassing. He's been criticized for jumping to conclusions, for seeking attention, for being insufficiently skeptical. But he's also been right about one thing. We don't investigate these objects thoroughly enough. We observe them, we catalog them, we publish papers, and then we move on. We don't send probes. We don't get close-up data. We don't answer the hard questions. Most astronomers still favor natural explanations for 3I Atlas. They argue that interstellar comets might simply be built differently than solar system comets, that they might have different ice ratios, different porosity, different structural integrity. We've only studied 3 of them. That's not enough data to define normal. Maybe interstellar comets are tougher, more resilient, because they've been cold-welded by millions of years at near-zero temperatures. Maybe they have different formation histories, different compositions, different responses to solar heating. But here's what frustrates the scientific community. We had a chance to get close, and we didn't take it. Several teams proposed rapid response probe missions to intercept 3I Atlas while it was still accessible. These missions would have been expensive and risky, requiring fast development and launch windows measured in months, not years. They would have involved off-the-shelf technology, small spacecraft launched on existing rockets, flyby missions designed to capture images, spectra, and compositional data from close range. The proposals were rejected, deemed too speculative, too uncertain. Funding agencies wanted more conventional projects, missions with guaranteed scientific return, not high-risk gambles on enigmatic visitors. So now, we're stuck observing from a distance, watching an object that may be the most scientifically significant visitor we've seen in a generation, and all we can do is point telescopes at it and wonder. When science can't look closer, imagination rushes in, and that's where things get dangerous. Within hours of the first detailed observations of 3I Atlas, the internet did what the internet does best. It built a mythology. Forums lit up with claims that the object had changed course. YouTube videos dissected trajectory data, overlaying red circles and arrows onto orbital diagrams, insisting that the object's path had deviated in ways inconsistent with natural gravitational perturbations. The word propulsion started appearing in comment sections. People began asking whether 3I Atlas was under intelligent control, whether it was a probe, a vessel, a warning. Let's be clear. The trajectory has not changed unexpectedly. Orbital mechanics is precise. When an object enters the solar system on a hyperbolic trajectory, its path is determined by its velocity and the gravitational fields it encounters. We've been tracking 3I Atlas since its discovery, and its orbit matches predictions based on Newtonian physics and relativistic corrections. Any perceived deviations are either measurement, uncertainties, or misunderstandings of how orbital projections work. Orbital calculations involve uncertainties. When astronomers first detect an object, they have limited data, maybe a few nights of observations. The calculated orbit has error bars, ranges of possible paths. As more observations accumulate, those error bars shrink, and the predicted path becomes more accurate. What looks like a course change is often just the orbit becoming better defined. The object isn't moving differently. We're just measuring it better. But that doesn't stop the speculation. And honestly, it's not hard to see why. Humans are pattern recognition machines. We evolved to see faces in clouds and predators in shadows because false positives kept us alive. If you thought that rustling in the bushes might be a tiger and it turned out to be the wind, you survived. If you assumed it was the wind and it turned out to be a tiger, you didn't. Natural selection favored paranoia, favored the ability to detect patterns even when they weren't there. When we encounter something genuinely strange, something that defies easy explanation, our brains automatically search for narratives, for agency, for meaning. We want to know why. We want to know what it means. We're not satisfied with "we don't know yet" because uncertainty feels dangerous. Add to that our apocalyptic memory. Every few generations, humanity convinces itself that the end is near. Halley's Comet in 1910 triggered mass panic. People thought the tail would poison the atmosphere. Some bought gas masks. Some threw parties. Some prayed. Newspapers fueled the hysteria, printing sensational stories about cyanogen gas in the comet's tail. Never mind that the tail is so diffuse that breathing it would be less toxic than standing next to a smoker. The fear was real. When Oumuamua appeared in 2017, speculation about alien technology exploded within days, fueled by its unusual shape and trajectory. The fact that it was accelerating slightly as it left the solar system, combined with its elongated, possibly pancake-like shape, led some to suggest it might be a light sail, a thin, reflective sheet pushed by sunlight or stellar radiation. Loeb wrote a book about it. The scientific community pushed back, offering alternative explanations involving hydrogen icebergs or nitrogen ice. 3I Atlas has all the ingredients for a viral panic. It's rare. It's unpredictable. It's happening during a planetary alignment that already sounds ominous. And it's arriving at the start of 2026, a year that numerologically minded people have been flagging for years. The number 2026 doesn't have any particular significance, but humans love finding patterns in numbers, and any year can be made to seem prophetic if you squint hard enough. Social media amplifies these loops. An amateur astronomer posts a speculative thread. It gets retweeted by someone with a larger audience. A YouTuber makes a video adding dramatic music and ominous voiceovers. The algorithm promotes it because engagement is high, because people are clicking, commenting, sharing. Within 72 hours, millions of people have been exposed to a narrative that treats speculation as fact. The problem is that these narratives become self-reinforcing. Once a critical mass of people believes something, it becomes harder to correct. Debunking doesn't spread as fast as the original claim. People remember the exciting story, not the boring correction. And some people actively resist correction because the narrative fulfills an emotional need, a desire for significance, for meaning, for the sense that we're living through something important. But here's the thing. Conspiracy theories are often emotional processing in disguise. When people feel powerless, when they sense that something big is happening, but institutions aren't being transparent, they construct alternative explanations. It's not stupidity. It's a coping mechanism. It's an attempt to regain a sense of control, to understand a world that feels increasingly chaotic and unpredictable. The healthy response is not to mock or dismiss, but to distinguish what we know from what we don't. We know 3I Atlas is real. We know it's behaving unusually. We know it survived perihelion. We don't know exactly why. We don't have close-up data. We don't have answers to every question. Admitting uncertainty is not weakness. It's honesty. And while the internet spins theories, while people argue in comment sections and make predictions about doom, the sun is doing something of its own. If you want to understand what's really happening in late 2025 and early 2026, stop looking at the planets and start looking at the sun. Solar cycle 25, the current phase of the sun's roughly 11-year activity cycle, is reaching its peak. This is when sunspot numbers surge, when magnetic field lines twist and snap, when the sun's surface becomes a chaotic mess of eruptions and flares. The sun is a magnetized plasma ball, and its magnetic field is constantly evolving, driven by convection currents deep in the solar interior. As the field lines tangle and reconnect, they release enormous amounts of energy in the form of flares and coronal mass ejections. The solar cycle itself is a fascinating phenomenon. It's driven by a process called the solar dynamo, where the sun's rotation and convection combine to generate and amplify magnetic fields. The sun doesn't rotate as a solid body. The equator spins faster than the poles, completing a rotation in about 25 days, compared to 35 days at higher latitudes. This differential rotation stretches and twists magnetic field lines like rubber bands being wound tighter and tighter. Eventually, they become so tangled that they break through the surface, creating sunspots, those dark patches that mark regions of intense magnetic activity. Late 2025 saw multiple M-class flares, events that release energy equivalent to millions of hydrogen bombs. Several X-class flares followed, the most powerful category we have. An X-class flare can release as much energy as 1 billion megatons of TNT in a matter of minutes. That energy doesn't just disappear. It radiates into space as X-rays, ultraviolet light, and particles traveling at a significant fraction of the speed of light. To put this in perspective, the largest solar flare ever recorded was the Carrington event of 1861, an X-class flare so powerful that it caused auroras visible as far south as the Caribbean. Telegraph systems worldwide experienced failures, with some operators reporting sparks jumping from their equipment. If a Carrington-level event happened today, the economic damage could reach trillions of dollars. Our civilization is far more dependent on electronics, satellites, and power grids than it was in the 19th century. These aren't abstract threats. They're physical events with real consequences. When a solar flare erupts, it sends a blast of X-rays and ultraviolet radiation toward Earth at the speed of light. 8 minutes later, that radiation slams into our atmosphere, ionizing particles in the upper layers and disrupting radio communications. High-frequency radio, the kind used by aviation and maritime services, can be completely blacked out on the sunlit side of the planet. GPS signals degrade because they rely on precise timing, and ionospheric disturbances introduce delays that throw off the calculations. The ionosphere is a layer of the atmosphere between about 80 and 1,000 kilometers altitude, where solar radiation strips electrons from atoms, creating a soup of charged particles. Radio waves bounce off this layer, which is how long-distance radio communication works. But when a solar flare dumps extra energy into the ionosphere, the layer becomes turbulent, unpredictable. Radio waves that should bounce get absorbed instead. Signals that should travel thousands of kilometers fade out after a few hundred. If the flare is accompanied by a coronal mass ejection, a billion-ton cloud of magnetized plasma, that cloud takes 1 to 3 days to reach us. When it hits, it compresses Earth's magnetosphere, the magnetic bubble that protects us from cosmic radiation. This compression has cascading effects. Satellites in low Earth orbit experience increased drag as the upper atmosphere heats and expands. Radiation levels spike, potentially damaging sensitive electronics. The magnetosphere is our first line of defense against the hostile environment of space. Without it, solar wind would strip away our atmosphere over millions of years, the way it did to Mars after that planet lost its global magnetic field. But the magnetosphere isn't static. It breathes, expanding and contracting in response to solar wind pressure. When a coronal mass ejection hits, the magnetosphere can compress. to half its normal size on the day side, while the night side stretches out into a long tail. Airlines reroute flights over polar regions, where radiation levels spike and communication becomes unreliable. Astronauts on the International Space Station take shelter in more shielded sections of the station. Power grids in northern latitudes, where geomagnetic induction is strongest, face the risk of transformer damage from induced currents. In 1989, a geomagnetic storm knocked out power across Quebec for 9 hours, leaving millions without electricity in the middle of winter. That Quebec blackout happened because geomagnetic storms induce electric currents in long conductors, like power transmission lines. These currents aren't supposed to be there. They're called geomagnetically induced currents, or GICs, and they can saturate transformers, causing them to overheat and fail. A single damaged transformer can take months to replace because they're custom built for specific installations. If multiple transformers fail simultaneously across a region, the cascading blackout could last for weeks or months. We've gotten better at predicting these events. AI-based space weather forecasting models now analyze solar imagery in real time, identifying precursor patterns that suggest an imminent flare or ejection. Machine learning algorithms trained on decades of solar observations can recognize the magnetic configurations that tend to produce flares. They can't predict exactly when a flare will occur, but they can identify high-risk regions and issue warnings hours or sometimes days in advance. These AI systems process data from multiple spacecraft, from the Solar Dynamics Observatory that watches the Sun continuously, from the Solar and Heliospheric Observatory, positioned between Earth and the Sun, from sensors on the Deep Space Climate Observatory, stationed at the L1 Lagrange point. They analyze magnetic field topology, plasma flows, sunspot evolution, and historical patterns to generate probabilistic forecasts. It's not perfect, but it's far better than what we had even a decade ago. But prediction is not prevention. You can see the storm coming, but you can't stop it. The best you can do is prepare, shut down vulnerable systems, reorient satellites, postpone spacewalks, warn airlines and power companies. And here's where planetary positions come back into the picture. The Sun doesn't exist in isolation. It sits at the center of a dynamic system where planetary magnetic fields, orbital resonances, and gravitational perturbations create feedback loops. Some researchers have proposed that planetary alignments can modulate the solar wind, the constant stream of charged particles the Sun emits. When planets cluster on one side of the Sun, the heliosphere, the bubble of solar wind that surrounds the entire solar system, might experience compression waves or density fluctuations. This is speculative, but it's not fringe science. The Sun is a plasma ball governed by magnetohydrodynamics, a field where small changes in initial conditions can produce outsized effects. Plasma doesn't behave like ordinary matter. It's electrically conductive, magnetically responsive, and prone to instabilities that can cascade in unpredictable ways. If planetary positions influence the heliosphere even slightly, and if the heliosphere couples back to solar surface activity through feedback mechanisms we don't fully understand, you have a potential mechanism for modulation, not causation, but timing. The solar wind isn't uniform. It varies in density, speed, and magnetic field strength. Fast streams overtake slow streams, creating compression regions where the plasma density spikes. These compression regions can trigger reconnection events in Earth's magnetosphere, releasing stored magnetic energy in bursts. If planetary alignments alter the structure of the solar wind, they might change the frequency or intensity of these events. Think of the solar wind as an ocean with currents and eddies and waves. When fast solar wind catches up to slow solar wind, it creates what's called a co-rotating interaction region, a compression zone that spirals outward from the Sun. These regions are sites of particle acceleration and magnetic turbulence. Earth passes through them regularly, and when we do, we often see enhanced auroral activity and minor geomagnetic disturbances. So when people ask whether the January 2026 alignment matters, the answer is maybe, but not in the way you think. It's not going to rip the planet apart. It might, however, create a window of elevated risk, a period when the sun is already active, the magnetosphere is already compressed, and Earth's tectonic systems are already stressed. It's about timing, about the convergence of cycles that are individually predictable, but whose interaction creates complexity. The sun will keep doing what it does, regardless of where the planets are. But if the planets modulate the timing, if they shift the probability distribution even slightly, that could matter during a period when we're already at the peak of the solar cycle, when the sun is already producing major flares weekly, when Earth's magnetosphere is already being battered by solar storms, and we haven't even talked about the potential coupling between space weather and terrestrial weather, between solar activity and atmospheric circulation patterns, between cosmic ray flux and cloud formation. These connections are controversial, poorly understood, and potentially significant. There's evidence that solar cycles correlate with certain climate patterns, though the mechanisms remain debated. If the sun influences Earth's atmosphere, and if planetary alignments influence the sun, you have a chain of interactions that becomes very difficult to model. Now imagine pairing all of this with an AI that sees what humans miss. Astronomy is no longer a field dominated by humans staring through telescopes. It's becoming a field where algorithms find the anomalies first. Artificial intelligence is revolutionizing how we detect and analyze celestial objects. Machine learning models trained on millions of images can identify patterns that would take human observers years to notice. In 2025, AI systems flagged 3I Atlas's jet wobbling before astronomers knew to look for it. Outgassing anomalies were detected by neural networks analyzing spectroscopic data in real time, producing alerts that prompted follow-up observations. The speed at which this happens is staggering. A human astronomer might spend hours examining a single spectrum, looking for emission lines, absorption features, compositional signatures. An AI can process thousands of spectra per second, comparing each one against a database of known patterns, flagging deviations, and prioritizing which objects deserve immediate attention. This isn't just faster, it's a fundamentally different way of doing science. This is incredibly powerful. AI can process data faster than any human team, scanning thousands of images per hour, identifying transient events, classifying objects, flagging anomalies for further study. It can recognize correlations across vast datasets, connecting observations from different wavelengths, different telescopes, different times. It doesn't get tired, doesn't get distracted, doesn't have confirmation bias, at least not in the traditional sense. Consider the scale of modern astronomy. The Large Synoptic Survey Telescope, now called the Vera Rubin Observatory, will produce about 15 terabytes of data every night once it's fully operational. That's thousands of images containing millions of objects. No human team could process that volume, but AI can. It can identify supernovae within hours of explosion, track asteroids that might threaten Earth, detect gravitational lensing events, and find objects that don't fit any known category. But it also introduces new risks. Machine learning models inherit the biases of their training data. If an AI is trained on solar system comets, it might flag interstellar objects as anomalous simply because they're unfamiliar, not because they're truly unusual. The model has learned what normal looks like based on thousands of examples, and anything outside that distribution gets marked as weird. But weird doesn't always mean interesting. Sometimes weird just means different. This is a subtle but crucial problem. AI doesn't understand context the way humans do. It recognizes statistical patterns. If you train a model on 100,000 images of cats and then show it a picture of a dog, it will flag the dog as anomalous. It's not wrong exactly, but the anomaly doesn't necessarily mean anything important. The same principle applies to astronomy. An interstellar object is anomalous compared to solar system objects, but that doesn't automatically make it artificial or significant beyond its interstellar origin. False positives can flood research pipelines, wasting time and resources. If an AI flags 100 objects as potentially interesting, and only one of them turns out to be scientifically significant, you've spent 99 times more effort on dead ends than on discoveries. Astronomers have to triage to decide which alerts are worth following up on, and that requires human judgment. The economics of telescope time make this even more critical. Major observatories are oversubscribed by factors of 5 or 10. For every hour of observation granted, there are 4 or 9 hours of proposed observations that get rejected. If AI-generated alerts consume telescope time chasing false positives, real discoveries might be delayed or missed entirely. The challenge is calibrating the AI's sensitivity, finding the sweet spot between catching everything interesting and drowning in noise. There's also a deeper philosophical shift happening. For most of human history, discovery meant understanding. You found something, you studied it, you explained it. Galileo saw moons orbiting Jupiter and understood it meant not everything orbited Earth. Hubble observed galaxies receding and understood the universe was expanding. Discovery and comprehension were intertwined. The process was linear. Observe, hypothesize, test, understand. Newton saw an apple fall and developed a theory of gravity that explained not just apples, but planets and moons. Darwin observed finches and developed a theory that explained the diversity of all life. Einstein thought about observers on trains and developed relativity. Each discovery came packaged with an explanatory framework. Now we're entering an era where discovery precedes understanding. An AI can tell you that something is statistically unusual without telling you why. It can find patterns without context, correlations without causation. It can say, this object doesn't fit the model, but it can't tell you what that means. It can identify the anomaly, but it can't interpret it. This creates a new kind of scientific uncertainty. We have more data than ever, more discoveries than ever, but we're not necessarily gaining understanding at the same rate. We're accumulating mysteries faster than we can solve them. The catalog of known exoplanets grows by hundreds per year, but we still don't fully understand how planetary systems form. We've detected gravitational waves, but we're still working out the details of black hole mergers. We've found fast radio bursts, but their origins remain debated. 3i Atlas is a perfect case study. If you fed all the observational data into a sophisticated anomaly detection algorithm, data on coma size, polarimetry, composition, activity duration, survival rate, trajectory, would it flag the object as high priority? Almost certainly. Each individual measurement might fall within plausible ranges, but together they create a profile that sits outside the expected distribution. The combination is unusual. An anomaly detection algorithm would look at the multivariate distribution of properties. Coma size alone might not trigger an alert. Survival rate alone might not either. But when you combine large coma, unusual polarimetry, unexpected composition, prolonged activity, and survival through perihelion, the compound probability becomes vanishingly small if you assume it's just a typical comet. The algorithm would flag it because the likelihood of all these properties appearing together by chance is statistically improbable. But what does that mean? Is it evidence of something extraordinary, or just the natural variance of a population we barely understand? We've only observed 3 interstellar objects. That's not enough to build a robust statistical model. Maybe all interstellar comets are like this, resilient and active and compositionally distinct. Maybe 3I Atlas is perfectly normal for its class, and we just don't know it yet. This is the fundamental challenge of small sample sizes. In statistics, you need dozens or hundreds of examples to define normal. With 3 data points, you can barely draw a line, much less understand the full distribution. Every interstellar object we've seen has been unusual in some way. Oumuamua was elongated and accelerating. Borisov was relatively normal, but carbon monoxide rich. 3I Atlas is tough and active. Are these 3 different flavors of normal, or are they genuinely bizarre? This is where human judgment becomes critical. AI can identify what's unusual, but humans decide what's important. We interpret, we contextualize, we exercise restraint. We resist the urge to leap from "this is weird" to "this is proof." We ask follow-up questions. We design new observations. We build models to test hypotheses. Humans bring domain expertise, intuition, and the ability to reason about causation. We can say, "This anomaly is interesting because it challenges our understanding of comet formation," or "This anomaly is probably just measurement error." We can design targeted observations to test specific hypotheses. We can integrate information from multiple fields, connecting astronomy to geology to plasma physics in ways that AI, trained on narrow datasets, cannot. And yet, the temptation is always there. When you're staring at an object that defies easy explanation, that arrived during a rare planetary alignment, that coincides with heightened solar activity and seismic unrest, it's hard not to wonder if there's a deeper connection. Not a mystical one, not a predetermined fate, but an emergent synchronization, a convergence of cycles that produces moments of heightened complexity. Complex systems exhibit emergent behavior, patterns that arise from the interaction of many components, but can't be predicted by studying those components in isolation. Weather is emergent. You can't predict a thunderstorm by studying individual water molecules. The solar system is a complex system. Planets, the sun, magnetic fields, solar wind, cosmic rays, interstellar visitors. They all interact in ways that create feedback loops and nonlinear dynamics. Emergence is one of the most profound concepts in modern science. It explains why consciousness arises from neurons, why economies behave unpredictably despite individual rationality, why ecosystems collapse suddenly after gradual stress. Small changes cascade, feedback loops amplify, and the system transitions to a new state that nobody predicted. The solar system, despite appearing orderly and predictable, is also a complex system capable of emergent behavior. 2026 is shaping up to be one of those moments where multiple cycles converge. The solar maximum, the planetary alignment, the passage of an interstellar object, ongoing tectonic stress on Earth, these are all independent processes, but they're happening simultaneously, and their interaction might produce effects we haven't anticipated. Each process has its own timescale. Solar cycles run 11 years. Planetary alignments recur on century scales. Interstellar visitors are sporadic, unpredictable. Tectonic stress builds over decades. The fact that these cycles are converging in January 2026 doesn't imply causation, but it does create a unique configuration, a moment when the system is in a state it hasn't been in for 90 years. Earth may not be waking up in any literal sense. The planet has been awake for 4.5 billion years. Tectonic plates have been shifting. Volcanoes have been erupting. Earthquakes have been shaking the ground since long before humans existed. But we might be waking up. We might be entering a period where our tools are sensitive enough, our data rich enough, and our pattern recognition, both human and artificial, sharp enough to see synchronicities we've always missed. The universe has always been dynamic. Earthquakes have always happened. Solar flares have always erupted. Planets have always aligned. Comets have always visited. What's different now is that we're watching all of it simultaneously, in real time, with unprecedented precision. We're connecting dots across disciplines, asking questions that span geology, astrophysics, and information theory. We're building models that integrate data from seismometers, magnetometers, telescopes, and satellites. We have instruments on the ground, in orbit, on other planets, at the edge of the solar system. We're monitoring Earth's magnetic field continuously. We're tracking every near-Earth asteroid. We're scanning the sky for transient events every night. We're analyzing the solar wind in real time. This integrated, multi-scale observation is historically unprecedented. Previous generations of scientists studied their domains in isolation. We're seeing the connections. And sometimes, when you have enough data, when you have enough perspectives, you start to see patterns that were invisible before. Not conspiracies, not prophecies, but emergent structures. Moments when the complexity of the system produces something unexpected. So when you hear warnings about 2026, about alignments and interstellar visitors and seismic unrest, don't dismiss them as fear-mongering. But don't accept them as prophecy either. Treat them as invitations to pay attention, to ask better questions, to acknowledge that the cosmos is far stranger and more interconnected than we've given it credit for. Because whether or not January brings catastrophe, whether or not Three-Eye Atlas holds secrets we can't yet fathom, one thing is certain. We're living through a convergence, a moment when Earth, Sun, planets, and an interstellar intruder are all doing something unusual at roughly the same time. The scientific method requires skepticism, but it also requires curiosity. We should question extraordinary claims, but we should also remain open to the possibility that reality is more surprising than our models predict. We should seek evidence, but we should also acknowledge the limits of our current understanding. The history of science is filled with moments when the universe surprised us. Quantum mechanics revealed that reality is probabilistic at small scales. Relativity showed that space and time are flexible. Dark matter and dark energy forced us to admit that 95% of the universe is invisible to us. Each discovery humbled us, expanded our perspective, reminded us that nature is under no obligation to conform to our expectations. And the energy shift is not coming. It's already here. The question is whether we're ready to see it.